All right, let's take a look at precipitation reactions. And they're not necessarily a class of reactions, but they're referred to precipitation reactions. And so you commonly know these as you'll see these as a double displacement or double replacement reaction. Okay, RXN just an abbreviation for reaction. So whenever you think about a double displacement reaction, replacement, because you'll have, remember you have two cations, and so you'll have one cation will displace and then replace the other one. So what happens is they displace and replace each other in the chemical reaction, the two cations, the two positive ions, right? And then that'll move over to the products. So here it says illustrate and explain what occurs during that. So if you think about it, what we usually get is something like this, all right? And you know, any sort of, wow, that's pretty horrible. Any sort of little diagram that shows where, you know, you just need a beaker. You could use a little Erlenmeyer flask, use a Dixie cup, it doesn't really matter. All right. So we've got two solutions. So we've got solution one, we've got solution two, whatever they're made out of, right? They're just two solutions. We've got some ionic compounds that are dissolved in water. And so remember, whenever that's the case, you have an aqueous compound, right? So it means, you know, you've got a solution of it. It's aqueous. You've dissolved in it. So that means you have free ions, right? Both cations and anions that are in solution. So if you were to combine these two together, so let's just say we pour all of this into there, and this second beaker is large enough to hold that entire volume, right? So we would say that there would be some sort of reaction that would occur, and then what we would have would be a combination of those two solutions. So if there's a precipitate, then that means that you're going to get some particles that all of a sudden start showing up. So all I'm doing is sort of stippling. I'm just putting a bunch of dots here. So you suddenly start to see it'll fall out of solution, literally where the two solutions meet. You'll see what looks like liquids forming. So if you look over here, both of these things look like liquids, just like water usually, right? The exception if you have like a copper compound, because copper compounds tend to be like blue. So typically you're going to get these two clear aqueous solutions. And when you mix them together, what happens is you'll start to see you'll start to see what looks like particles falling out of the solution, precipitating down, and they'll settle out at the bottom. And then eventually, as the reaction stops and all the molecular motion of the solutions mixing back and forth and moving and particles bouncing off of the inside of the beaker and that type of stuff, and everything settles down and it looks like the water's staying still, then you'll see all these particles at the bottom. Now I just chose the color blue just so that you could see a difference. So what you do need to keep in mind is so this right here would be your precipitate. So sometimes you'll hear the word precipitate and precipitate. So precipitate tends to be used if it's like the verb, like the action of it precipitating. So like rain is called sometimes precipitation because literally that water will come together and fall out of the atmosphere. It'll precipitate down. And then precipitate tends to be a way of saying it to identify that you're talking about the noun. So if you were to pick up some of these particles right here, you'd say, here's the precipitate right here. There's the precipitate. I'm holding some precipitate. Usually you won't grab it by your hands. You don't ever do that. But I'm just trying to illustrate that. And so then right here is, so you have these two solutions. So if you think about it, you have cations and anions in this solution, and you have cations and anions in this solution. And so remember, we've said that the cations swap. They tend to displace and replace each other, right? So what that means is this the precipitate here will be a combination. It will be some sort of ionic compound where you have your cation and anion that comes together in this solution, can chemically combine. They were first separated, so it doesn't matter if we're talking about number 1 or number 2. The positive ions and negative ions that were in number 1, they were able to stay in solution. They were able to stay dissolved. They were soluble in the water, typically distilled water or deionized water. And then here in solution 2, the cations and anions were able to stay separated, and so you had an aqueous solution here as well. Once we mix them together, then what happens is these ions are free moving and floating, and as they bump into the anions that were in the other solution, you tend to sometimes get this reaction that occurs. And when that occurs, sometimes the cation that's in one solution, when it mixes with the anion in the other, will form an insoluble compound. So your precipitate is the insoluble compound. All right, it's the insoluble compound. And then this right here would be, this right here stays in solution. So this is the, we're going to say the new aqueous solution. Okay, and there's some other terms for both of these, and we'll get into that in some later videos, but right now we just need to know the basics right here. So in the other videos, I'll address some of these terms for you. So the new aqueous solution, so a different set of cations and anions that are together as a result of solution 1 and 2 here mixing, and then when the new cations and anions come together that are insoluble, they precipitate out of solution and fall to the bottom. That's the precipitate. All right. So let's take a look at an example down here. All right. So it says solutions of calcium chloride and sodium nitrate are combined into a beaker. So before we go any further, let's just write that compound for that. So calcium chloride, we know, is CaCl2, and it tells you solutions of both of these. So let's just go ahead and put our phase labels. We already know we have a solution of it. And then sodium nitrate, so that's NaNO3. We obviously have a solution of it, just going to put AQ, right? So we pretend both of these are in our beaker, we pour them together into one container, and then all of a sudden they swirl around. And remember what we did up here, we said that you have a cation and an anion. There's our cation, there's our anion. Calcium here is the cation, chlorine is the anion. And this one over here you have a cation and an anion. Sodium is the cation. The nitrate, the polyatomic ion, that is the anion. So let's do a little bit of scratch work off to the side, okay, shall we? So I'm going to do some scratch work, then I'll erase the scratch work, right? So what we basically have is these ions in the first solution, and then we have these ions in the second solution. And then according to what we've talked about, this cation and this cation displace and replace each other, right? So what that means is if we think about it, we can keep the anions where they already were, because we think about them not moving. Now it doesn't matter what order you put this stuff, but I've noticed if you get into a pattern, a habit of doing things a certain way, you're going to make less mistakes, and it makes it easier to process this when you're first learning it. Okay, even after you've done it for a while, you'll be less prone to error. So sodium is now displaced and replaced over here where calcium is, so that means we have sodium ions over here with chloride ions, and the calcium displaced and replaces sodium over here, so that means we have calcium ions over here with nitrate ions. So now we think about this, we know this is sodium chloride, and we look at this right here, we go Ca2 plus, NO3 negative, so we've got a positive 2 and a negative 1, right? So if you think about it, positive 2, negative 1, you are going to need 2 of these negative ones and 1 of these so that it balances out. Remember, we want the oxidation numbers to be 0. So the formula here would be we would need 1 calcium, right? 1 calcium, and we need 2 nitrates. So there's 1 nitrate, polyatomic ion, put in parentheses so that nothing gets misunderstood. And then there's our 2. Because 1 nitrate ion, remember, is NO3 negative, and that doesn't break up. So according to this, we have sodium chloride, and we have calcium nitrate. All right. So both. So there's our scratch work. I'm going to go ahead and get this scratch work out of the way. You can always reverse the video and go back and take a look at this if you need to. So this information is always going to be there for you. Right? So now, oops. So I'm just going to move this out of the way just a little bit for you. I'm going to bring this over here, and I'm just going to move this over here away from the video part because we may have some more writing we have to do. Okay, so now what we have to figure out is which one of these is our precipitate and which one is aqueous. So again, go back to your reference sheet, right? And so you've got your solubility guidelines here. All right, so let's zoom in. And so remember we said we've got sodium chloride. So we come back over here and we look down here. And so this table is broken up into 2 parts. So the first part is what is soluble and what is not soluble, insoluble. So you look at it one at a time. And then this column here is just what are the exceptions. So if something says it's soluble, but there is an exception that applies, then that would be the opposite, that'd be insoluble. And the same is true for the insoluble part. If you follow this part here and you see that it's insoluble, then if there is an exception, then it's the reverse, it is soluble. So we look down here, sodium chloride. So chloride salts are soluble. The exception is when they're with silver, mercury 2, or lead 2. Well, it's with sodium, so it's going to stay soluble. So we come over here, and since we know that this is soluble, and of course this is just basic like table salt, right? So you already knew table salt it would dissolve in water. People do that all the time for like when they're sick and they got strep throat, right? And they gargle with salt water. But we just verified that using the solubility rules. All right, now we've got calcium nitrate. So we go back to our table, and nitrate salts are soluble, and there are absolutely no exceptions. So according to this, it is soluble. So we go back and we realize that this substance is also soluble. So according to this, we have a solution here and a solution here. When we mix these two together into one container, so basically what we did was we took this and we took this and we put them into one larger container, right? So here's where it's mixed together, and we basically see nothing. There's no precipitate according to this. According to this, the 2 products are aqueous. And so when that happens, then there's no reaction. So when this happens right here, once you identify the phase labels for both of these as this, then essentially you just come down and you say no reaction. All products are soluble. Okay, pretty easy. All right, let's take a look at another one. So again, not everything that comes into contact is going to be a reaction. Remember, this goes back to your basics that you learned in the first part of chemistry. So no reaction is a chemical property. All right, not everything. If everything reacted, it would be impossible for us to kind of have a lot of modern society the way we have it. If you think about it, when we build houses, we put things together. We build cars, we put things together. If everything reacted when it came in contact with each other, nothing could stay separate. So that's a highly important property. All right. All right. Let's take a look at this one. Let's take a look at this one. Solutions of barium chloride. All right. Again, you should be able to write this without me having to explain it. Again, if you can't, go find the videos where I talk about how to do ionic compounds, stuff like that, and review all that. So there's barium chloride and sodium carbonate. So it's Na, and then that would be a 2CO3, and it says solutions of these, so we're going to go AQ. All right, so remember we've got BaCl2 plus, oh, I'm sorry, scratch work. So here is, we're thinking of our ions, right? And so we're mixing all of these together here. So that means we have this ion and we have this ion. Okay. So barium and the cations, remember, they swap. They displace and replace each other. The anions, we think of them as not doing the displacing and replacing. So I recommend what you do is you just keep those ions where they already were. And again, this is just scratch work right here. Right? This isn't the actual reaction itself. So sodium is now over here with chlorine, and barium is now over here with the carbonate, right? Okay. All right, so according to this, we have sodium chloride. We kind of already know the answer for that one. And then we've got barium carbonate, right? So we come up here, we put NaCl plus BaCO3. I'm going to get rid of my scratch work, because on a quiz or a test, this scratch work would be somewhere else, unless you're specifically told to show it in that problem, right? All right. So, we already did the legwork up here where sodium chloride, we saw that those chloride salts, especially with this one in particular, would be aqueous. So we can put AQ, and we know that's going to happen. So now let's look at the carbonate, right? So we come over here, we find carbonates, CO3. Carbonates are insoluble. They're insoluble. So according to this, insoluble means it will precipitate out of solution. Now there are exceptions. The exception is with an alkali metal or ammonium. So there's no ammonium in this, so we don't have to worry about ammonium. So here's where you have to remember the difference between an alkali metal and an alkaline earth metal. So remember, the alkali metals are your group 1 elements, and your alkaline earth metals are the group 2 elements. You just have to remember that. So according to this, if the carbonates are insoluble, except if they're with an alkali metal. So if it was with an alkali metal, then it would be the opposite, which would be soluble. But it's not. It's with a group 2 element. So we go back here, and we realize that this right here is our precipitate. So the way you show that is a down arrow. It is solid, and so you will sometimes maybe see people when you're first taught this to write an S for the solid, but we put the down arrow because what that signifies is that this particular compound that's insoluble fell out of solution. All right, and so we tend to think of things like that falling. So right here, this is, there's your precipitate. All right, so sometimes there's a reaction, sometimes there's not. So if there's no reaction, then you just basically go below it and say, no reaction. All products are soluble. That's pretty easy. If you're in the honors class, we're going to do some other stuff besides this, where we'll identify examples like this, where there is no reaction, and where there is a reaction. There's going to be some other ways we're going to write this. Generally speaking, if all you have to do is this part here, then this is all that's needed. All right, and then of course you need to, I didn't write balanced reactions, right? So you would always want to go back and balance your equations. These are just skeleton equations, just looking at the concept of whether or not you do or do not get a precipitated forms. All right. Hope that helped. I'll leave down in the comments. I'll leave links to different parts of the video so you can easily skip to and from different places and review what you need to. Hope that helps, and look forward to look for the next videos where we'll take something like this and we'll do some stoichiometry with it and stuff like that. So, bye. Hang in there.